hello. Today we're going to talk about some things that are going to seem fairly obvious to you, I think. If you've ever seen a door open or a gate or anything with a hinge, you've probably already figured this out. If you've ever seen a pennant, if you've ever seen a triangle, you very possibly have figured out what we're about to point out. Let's see how they wrote this. If one side of a triangle is longer than the other side, then the angle opposite the longer side is larger than the angle opposite the shorter side. Wow, it's a mouthful. What does all that mean? Well, really a lot simpler than how it sounds. All it's saying is find the long side of the triangle. Like in this case, it'll be this one here. Then that's the biggest angle opposite it. Conversely, down here, find the largest angle, which I think would be this one here. See, 30 and 50, so it'd be 100 degrees here. And this would have to be your longest side. For instance, I actually drew it in down here. Don't worry. I put the smallest angle in red, and there's the shortest side directly opposite. The largest angle is in blue, and there's the largest side directly opposite. And this is, if you think in terms of angles, probably kind of obvious to you. I mean, think of like a fence gate. When the gate is like that, you got nothing. When you pull it out here, you got this opening here, and you open it out that way. A larger angle produces a larger side here, and larger angle produces a larger side here. Anybody who's ever held a door open for somebody carrying a large box or a mattress has probably figured out both of these theorems without any trouble, and without actually taking a geometry class. We just had to put this in words so that later on we can use it. You can't just run around saying things are true in mathematics. In politics you can do that, not in mathematics. In mathematics you have to actually point to something and say, I have a theorem or a postulate that says this is definitely true, so now I can do it. In this case, we have now a specific theorem which tells you what you've probably known most of your life. If you open the door wider, the opening gets bigger. Now here's another one of those. Results that you would probably look at and say, well, what else could it be? Of course, this is true. And you'd have a point. But, as I mentioned before, we have to explicitly state things so that we can use them later. And this one here, the triangle inequality theorem, this actually gets used a lot. This is another one of those important theorems. I think I mentioned that right triangles get used a whole bunch. Well, the triangle inequality theorem doesn't get used as much as right triangles do, but it pops up over and over again. It gets used a lot. It becomes a part of many more advanced proofs in calculus, advanced calculus, or introductory analysis, however you want to look at it. And even in some other more advanced classes, you end up pointing to the triangle inequality theorem somewhere along the way to get from one step to the next. So this is a fairly simple result. It gets used in some actually complicated, sophisticated arguments, believe it or not. Kind of like the axiom of choice. I told you about that before. It's the one that says, given a group of objects, you can actually choose one. Well, that gets pointed to frequently in sophisticated proofs. This does too. The result is not very shattering, but it gets used a lot, so it's a good one to remember, both the name and what the heck it means. And what does it mean? Well, let's consider the distance from A to C, this line here. Well, I think we know a straight line would be the shortest distance between 2 points. You could put it that way. That's kind of what the triangle inequality says. It says that if you take any other root, and we're referring to straight line roots now. In fact, for a triangle, it would only be two different routes. You have one route and then you change direction. So two straight line routes will never be shorter than one direct line route. Look at it that way if you want. If you look at it that way, once again, you've probably known this all your life. If you were, no heck, if you played pickup football when you were really young, you knew where the goal line was. If it was down here and there was nobody in front of you, did you take off toward the sideline and then head back to the goal line? Or did you just run straight to the goal line and get there as quick as you could and save yourself as much energy as possible because you took the shortest route? Well, if you took this route to get to the goal line with nobody in front of you, I think you need to have a little talk with your coach. Doesn't sound like a good plan to me. This is the route most anybody would take, provided there's no obstacles you need to avoid. So everybody already knows this. We just have to give it a big name. That way it's part of mathematics. If it's something everybody knows, well, how can we call it mathematics? I mean, we do lots of smart stuff in mathematics, and if we're going to say that everybody knows it, then how does that make us smart? So we have to give it a big name. Triangle Inequality Theorem. And all it says is what you already know. The quickest way to get from here to here is to just follow the straight line. Any other route you take is going to be longer. In the case of inequalities, as I said, we're talking about two straight line routes, because that's what a triangle is. One thing you should keep in mind about these fairly obvious results, the previous two and this one, just because they're obvious doesn't mean they're easy to prove. It's an unfortunate aspect of mathematics. Sometimes the simplest and most obvious theorems are the hardest ones to prove. If you don't believe it, try to prove 2 plus 2 equals 4. It's not that easy to do. You end up using the rules of arithmetic, which would be a circular argument. In other words, you start out, in a sense, assuming that 2 plus 2 equals 4, and then you prove it. And of course, that's not a valid proof. A true two-column valid proof of the fact that 2 plus 2 equals 4 is not that easy, even though everybody knows it's true. Speaking of which, if you were going to do something like that, what would be the best way to approach it? Well, there is something called indirect proof. I don't like that name very much. I like the name proof by contradiction. I think it sounds more like what it is. For instance, if I want to prove that 2 plus 2 equals 4, maybe the easiest way to do that would be to assume that 2 plus 2 does not equal 4. And there's two ways it could not equal 4. It could be greater than 4 or less than 4. So let's take the case where 2 plus 2 is greater than 4. Well, suppose we subtract 2 from each side. Now we have that 2 is greater than 2. Oh, wait a minute. We have a property of equality. Remember the old POE? And one of those was the reflexive property of equality. And that says that anything is equal to itself. We have one for congruence also that says that every object is congruent to itself. Every number is equal to itself. So, 2 greater than 2, that can't happen. That's impossible. That's what you call a contradiction. So, if we assume that 2 plus 2 doesn't equal 4, we end up with a contradiction. And that is considered proof that it does equal 4. In other words, well, maybe not in other words, maybe just in exactly the same words. It's a subtle concept, but it's kind of simple once you get your head around it. Whatever it is you're trying to prove, you start out assuming that it's not true. And then you run down the line and see what that leads to. And eventually, if it actually is true, it should lead to a contradiction. For instance, here you get that a number is greater than itself. Well, that can't happen, so this can't be true. It cannot be true that 2 plus 2 does not equal 4. Why? Because it contradicts our reflexive property of equality. Okay, we found a contradiction to a rule that we know is true. If we contradict a rule that we know is true, we must have done something wrong before we got here. And what we did wrong was we assumed that 2 plus 2 wasn't equal to 4. That's called indirect proof. It's also called proof by contradiction. I like proof by contradiction, and that's probably what I'll call it from here on. Seems to me more like what it is. You start out by assuming the inverse of the hypothesis is true. And then you find, as you go down the line, you find a spot where that leads to an impossibility. This can't possibly be true because it leads to something else that can't possibly be true. And there are lots of simple things that you could prove aren't true by contradiction. Suppose I say water and gasoline are the same thing. How do you prove I'm wrong? Well, assume that I'm right. Say that water and gasoline are the same. Well, gasoline burns just fine, so if I throw a match in a puddle of water, it should ignite. Well, it won't do that, will it? Well, that's a contradiction, because water doesn't burn, and if water and gasoline were the same thing, then water would burn. So I found a contradiction. Water doesn't burn, so water and gasoline must not be the same thing. And here we're going to determine possibilities based on some of the things we just learned. Things which we now have theorems for, but you probably already knew. So let's fill in this angle first so we know what we're talking about here. Well, we know that the angles have to add up to 180, so we add these two and get 121. Subtract 121 from 180 and get 59. That's this angle here. Now they say, which is a possible side length for ST? It's this here. Well, now this angle is a little bit bigger than this angle. The side opposite this angle is 8, and in fact, this is the smallest angle in the triangle, so this is the smallest side, which means 7 wouldn't work. That's smaller than 8, and 8 is already the smallest part of the triangle. 8, well, that's a possibility, except that the angle here, over here, is not equal, which means this has to be bigger. And the only number here that's bigger is 9. So remember, we're not saying that this has length 9 because this is 59 degrees. We chose 9 because it's greater than 8. That's all we know. We know that it must be greater than 8 because 59 is greater than 56. Other than that, we don't know anything. That's why it says possible. So don't get those two confused. We have not found the length of ST. We have just determined that it has to be greater than 8. Now here I think they expect us to use our triangle inequality. That's the usual shorthand term for the theorem. It's not usually called the triangle inequality theorem. You usually just refer to it as the triangle inequality. It's so well known that it almost has a nickname. So, how do we do this? Would it be possible to construct a triangle this way? Well, you just have to remember that the sum of any two sides has to be greater than the other side. For instance, 6 plus 7, we can just write it out, I guess. 6 plus 7 has to be greater than 11. Well, that's 13, so that works. Now, 7 plus 11 has to be greater than 6. Don't think that could work. And what do we got left here? 6 plus 11 has to be greater than 7. Well, we got a problem here. These don't work. This is... Oh, pardon me. This does work. Wow. I can see this ain't going to be my day. 6 plus 7 is 13, which is greater than 11. 7 plus 11 is 18, which is definitely greater than 6. And here we get 17, which is greater than 7. So this works. You could draw a triangle that looked like this, that had sides 6, 7, and 11. Well, somebody could. I'm not sure I could. I'll give it a try. This is the shortest side. This is the side of length 7, and this kind of looks like a right triangle. There's no particular reason for that. I was just trying to match up the side lengths. Although if 7 squared plus 6 squared equals 11 squared, it might be a right triangle. You think it is? With these numbers? There's always a way to find out. Remember, we just used Pythagoras' theorem. So if we were to lay this out, could it be a right triangle? Well, let's find out. We got 7 squared is 49. 6 squared is 36. And does that with a question mark on top of it. 11 squared is 121. Well, this adds up to 85, and that's not 121. So, this squared plus this squared does not equal this squared, and this is not a right angle. But it is a possible triangle. These work. This part here, that wasn't part of the question. Here's another problem. Almost exactly the same. We're going to use our triangle inequality. Which group of side lengths can we use to construct a triangle? Well, I guess if we find one, we can stop. But I like to check and make sure that we've got stuff right. So let's convert these. That's the only difference between this problem and the other one, is that we have units here. So we got yards, feet, and yards. It'd probably end up with more whole numbers if we just convert the feet. So 3 yards would be 9 feet. 5 yards would be 15 feet. Over here, 3 yards. 9 feet, 5 feet, 8 feet. Inches, inches, and inches. Feet, inches, inches. Well, this is 24 inches, right? Now, can be used to construct it. Well, some of this we can just do in our head. For instance, 11 plus 12, that's 23. That's not longer than the third side here of 24 inches, is it? So, put an X next to that one. That won't work. What about this here? Maybe. The 8 and 5 is 13, that's bigger than 9. 9 and 5 is 14. That's bigger than 8. And 8 and 9 is 17. So this one would work. What about down here? Well, what do we got? 11 and 16 is 27. They can't be equal. That is a strict inequality. If they were equal, well, then it would just be the same side. If this was one side of the triangle, or two sides, however you want to look at it, we got an 11-inch side and then a 16-inch side. Where would the 27-inch side go? Oh, right on top of it. In which case, well, I drew that so badly. It's trying to imply that the 27-inch line would just go right on top of these two lines, which would just be connected together. In other words, this would just be a straight line. There's no triangle that would work with these dimensions. What about this? Well, I think you can see right off. 9 and 4 is 13. That's not greater than 15, is it? Just cross that one out, and here we are. This one would work. The others, I know it seems kind of a slow, boring, drudgery type process to determine if these can actually be triangles. And you're right, it is. But some of it, it's just simple arithmetic. You can do it in your head pretty quick. So it's not quite as bad as having to take a bunch of weird numbers and set up 3 different inequalities. If these numbers were more complicated, this was 185, this is 216.3, and this was 172.18, you'd have a lot more work to do. At least I would. Maybe you can do those numbers in your head, but it would take me a lot longer. But with these simple numbers, and hopefully you'll see a lot of those kind on your state exam, so you can, once you convert, be sure to convert. Don't forget, everything has to be in the same units. After that, you can probably do a lot of them in your head. Here is a simple little result, which I think could be called a corollary. Why? Well, what it says here is that the exterior angle of a triangle is greater than the measure of either of the non-adjacent interior angles. It's kind of a mouthful. What are they trying to say? No, it's just that theorem we had back in chapter 4, I think, which says that the exterior angle here is equal to the sum of these 2 angles. And remember why that would be. This angle and this angle are supplementary. They form a linear pair. But this angle plus these 2 angles also add up to 180. So we got this plus this equals 180, and this plus these 2 equal 180. So it was easy to show that this angle is equal to the sum of these 2. Well, that means it has to be larger than either one, unless one of these is 0. And in a triangle, none of the angles are allowed to be 0. They're also not allowed to be negative, but definitely not 0. Given that, there's just no way that this angle could be congruent to this angle. This angle has to be smaller than this one. Maybe not by much, but it has to be smaller by whatever this is. Okay. What about this over here? Let's see what he gave us. What did he come? I'm not even sure what it is he's saying here. Let's take a hard look at this. Well, if this is 59 degrees, then this must be 59 degrees. This is the largest side of the triangle. That means this has to be the largest angle. Does that make sense? Well, let's see here. If this is 59, then these 2 must add up. These 2 must add up to 180 minus 59, which I think is about 121. Yeah, I better double check that. Yes, the sum of these 2 angles is 121. So, what's the smallest either one of these angles could be? Because if this side is 17, that means 59 degrees has to be the largest angle in the triangle, because the other 2 sides are 15 and 16. Largest side of the triangle, opposite is the largest angle. Well, you can't have, well, let's just suppose that both of these, let's call them alpha and beta. Say that alpha we could lay it out this way. This is the largest angle in the triangle. Then let's call this alpha and this beta, just because it's easier to write. And I'm going to say the measure of this angle is alpha, and the measure of this angle is beta. That means I get to write less. let's say now we have to have that alpha is less than 59 and beta is less than 59 because this is the largest side. Well, if we add them together, we get that alpha plus beta is less than 59 plus 59, which is 118. Well, wait a minute here. Alpha plus beta we know equals 121. It has to. That's from our theorem that says that all the angles add up to 180. So, we assumed this was correct. We laid out an equation which follows directly from the assumption that this is correct, and our equation leads to a contradiction, which means this must be wrong. This cannot be the largest side, because at least one of these angles has to be greater than 59. And this was an example of proving this was incorrect by assuming it was correct and leading to a contradiction. Here they'd like us to describe the possible values of x. I'm not sure what they mean by that. I have a feeling they mean show the inequalities, show the range that within which x must fall for this to actually be a triangle, because we have some, well, in this section we have a property of triangles, which I think we can use to find the possibilities for x. We have to show that these two add up to more than this, these two add up to more than this, and these two add up to more than this. Well, let's write it out so it makes more sense. I went ahead and wrote these out because you'd probably fall asleep watching me write all this. And all I did was write the three inequalities which we know must hold. That is that this side plus this side, that is the length of this side plus the length of this side, is greater than the length of this side. Also, the length of this side plus the length of this side is greater than this. And same thing down here. This plus this is greater than this. So if I write all that out and solve the equation, I get that when I use this side and this side greater than this, I get that x is greater than 15. Any number smaller than 15 would not work. So I checked the others to see if I get a range, because I might end up with something like x is greater than 15 and x is, say, less than 17, so that the numbers between 15 and 17 would work. We'd have a range. This one didn't quite work out that way. Our next equation says that x has to be greater than 10 over 6, if I didn't mess up the arithmetic. And I may have. Yeah, seems to be right. This one says x is greater than 10 over 6, which is less than 2. Like 1 2/3. And we set up a similar equation here, that this side plus this side is greater than this side, and we get that x is greater than 2. Well, for this to work, all these have to be true. X is greater than 2, x is greater than 10 over 6, and x is greater than, x is less than 15. Oh, cool. We do have a range. That's what I was hoping for. This one says x has to be greater than 2. So this being, I don't know, it's approximately 1.66, I think. This is greater. That means that if I were to use this, like actually use 1.66 or some number between 1.66 and 2, it would satisfy one of the inequalities, but not the other two. We need something that satisfies all of them. Well, if x is greater than 2, it's certainly greater than 1.66. So this part doesn't contradict this, so we can use this. X is less than 15. So Now all we have to do is we just draw a little number line here. And we got 1.66 here, 2 here, and 15 here. X has to be between these two. Greater than 2 and less than 15. So there's our range. All this is acceptable for X. Since we have the triangle inequality, it's called an inequality for a reason. We can't say that X is actually equal to something, not unless we have more information about what these numbers, these side lengths actually are. So that's why we end up with an inequality. And those frequently lead to ranges, such as between here and here, as long as it's greater than 2 and less than 15. I didn't draw the line right out to the endpoints because it doesn't actually include the endpoints. X equal to 2, it wouldn't work. If X was equal to 2, then this side plus this side would equal this side, and that's no good. That would just lead to a straight line, not a triangle. The inequality is what's called a strict inequality. So 2 and 15 are allowed, but anything between 2 and 15 is cool. Here's one that looks kind of complicated at first, because we don't know what these lines are. I mean, if you're like me, you're probably thinking, well, is this a centroid? Are these medians that are intersecting here? So we know something about these lengths. What's going on? Well, none of that. This is just some arbitrary point. It means nothing. These are just arbitrary lines drawn from that point to the vertices. And the only reason for doing that was to produce 3 more triangles. We have this one large outer triangle here. By connecting this dot to the 3 vertices, we produce 3 more small triangles. And then we can use our triangle inequality to determine possibilities for the perimeter. Because what is the perimeter? Well, it's this side plus this side plus this side. So all we have to do is find limits for each of these sides, and we'll find limits for the perimeter of the whole triangle. It'll make more sense if we do it. And I think the biggest problem with using the triangle inequality is we end up with so much equations we run out of room. You've probably gone through paper like crazy doing these things. So let's apply our triangle inequality to these small triangles and see what we get. And just to save myself some writing, I'm going to relabel these as A, B, and C. Side A, side B, and side C. In fact, I'm going to let A, B, and C represent the length of these segments. That'll make it much easier to write out. So what do I have? I have the 3 plus 4, or 7, is greater than B. I hope you don't mind if I do this in my head. These are pretty small numbers. And I get 5 plus 4, or 9, is greater than C. Okay. And then I got 3 plus 5, that's 15. And that's greater than A. Now it's a lot of equations, but luckily they gave us simple numbers. So that our triangle inequality, when applied one way, will give us, as I pointed out, 7 is greater than B, 9 is greater than C. That's the 5 and 4 here, and the 3 and 8. I goofed. I multiplied 3 by 5 and got 15, of course. Which is the right answer, but that's not what we're supposed to be doing. I should be adding 5 and 3, and getting that A is less than 8. So, the perimeter, that would be the sum of A, B, and C, has to be greater than the sum of these 3 numbers, which is 24. So we have the perimeter, I should write it this way. perimeter is less than 24. We already know that it's greater than 0, but can we say more? Can we apply the rest of the triangle inequality and produce some more inequalities? It'll give us more information about these side lengths, and yes, we can. Here we could write that 4 plus c is greater than 5, and get that c is greater than 1. Here, same thing. We can have 3 plus b is greater than 4. And similarly, 3 plus a is greater than 5. So this gives us a is greater than 1, b is greater than 1, and c is greater than 1, pardon me, b is greater than 1, and a is greater than 2. Now, we could use our third equality to get even more limits, but it won't do any good. Just as you can check it out yourself or try it. If I change this from, instead of c plus 4 is greater than 5, how about c plus 5 is greater than 4? Well, if I do that, put a 5 here and a 4 here, I subtract 5 from each side and get that c is greater than minus 1. Well, we already know that because you can't have negative length. In fact, if this number is smaller than this number, I'm going to get negative numbers here. Which means that each of these sides, with the third set of equalities we could set up, we would show that each of these sides is greater than some negative number. Well, that doesn't add anything. That adds no information, because we already know that they're greater than 0. So we can stop right here. And what does this say? Well, this says that, put it this way, c plus a plus b plus c is greater than 1 plus 1 plus 2, which is 4. So it's less than 24 and greater than 4. Or we could write now that our perimeter is greater than 4 and less than 24. I think that's what they asked, wasn't it? Yeah, between what two integers? So the perimeter will be between 4 and 24. It's tempting to stop right here if you want to consider 0 an integer and say, well, it has to be between 0 and 24. But we have more equations, so it's a good idea to take a look and see if your extra equations will add information to the situation. In this case, it does. Without these equations, we wouldn't have this, and we'd have 0 at the left-hand end, and that's not quite right, because a number less than 4 would not work for the perimeter. Well, that's about it.